One more year and you'll be able to cross the street on your own. Very exciting. Okay, so we're finishing off this chapter today, doing 5.3, looking at the graph of tangent. We're going to see that it is quite a bit different than sine and cos. It's not sinusoidal. It doesn't have that wave shape to it. And we're also going to see that the period is different, as well as domain and ranges are different as well. And then on Monday, we'll have a quiz on chapter 5. And then probably Wednesday, we'll go through that quiz. And Thursday's the last day of classes, so that Wednesday will be our last class before Christmas. So that's the day you bring my presents to me.
Yes.
I'll be the last. Well, you know, what you got me last year, double it. That's fair. That's fair. So if you get me nothing, if you got me nothing last year, then double it.
So nothing?
But then you know what happens to your mark too, right? Doesn't double. It's inverse relation. It goes half. So no, because we have to do chapter 6. It'll be after Christmas. Yep. All right, so we're going to look at the graph of y equals tangent x. We'll talk about the characteristics of that graph. These graphs have asymptotes, so we'll see where those are, and then see some problems where we analyze the graph of y equals tangent x. So on the next page, we're going to graph tan theta between negative 2 pi and positive 2 pi. And so we've got a table of values there. Now the table of values is set up between 0 and 2 pi, but the tangent graph is periodic, so there is a period. It just looks different than the graph of sine and cos. So in this case, our theta values are in radians, so we're going to use our calculator to find the tangent of each of these angles. They have to be in radian mode. If you take the tangent of 0, you'll get 0. The tangent of pi on 6 is 0.58. The tangent of pi on 4 is 1. And that comes right from the unit circle. In fact, you can use the unit circle to get these values. You just have to write them as decimals so that we can put them on the graph. The tangent of pi on 3 is, from the unit circle, root 3, which is 1.73. Now, when you take the tangent of pi on 2, the unit circle said that it was undefined on our calculator, then we get an error there, because the tangent of pi on 2 does not exist. So we'll use the infinity symbol there. And then we can continue again using the calculator, but I'll just give you the values from here on in. At 2 pi on 3, it's negative 1.73. 3 pi on 4 is negative 1, then negative 0.58. At pi, it's 0. At 7 pi on 6, positive 0.58. Then 1.73. At 3 pi on 2, it's undefined. Negative 1.73, negative 1, negative 0.58, and 0. So again, those come right from the calculator or from the unit circle. You just have to write them as a decimal if you're using the unit circle so that we know where they are on the graph. So plot the points. I've got the point 0, 0. At pi on 6, so that this graph is set up for 6 pi on 6s, because this is 1, 2, 3, 4, 5, 6 sections between 0 and pi. So each one is a pi on 6, and you're going to get 0.58 just above 1.5. And then at pi on 4, which is a quarter pi, so in this case, because between 0 and pi is divided up into 6 sections, you have to take 1/4 of that. And 1/4 of 6 is same as 6 divided by 4. It's 1.5. So 1.5 units, we're at a value of positive 1, which is right there. And then at pi on 3, which is 2 pi on 6s, we're at 1.73, approximately right there. And then at pi on 2, which is 3 pi on 6s, it's undefined. And because of that, we're going to get a vertical asymptote at 90 degrees or pi on 2 radians. Then at 2 pi on 3, which is 4 pi on 6, we're at negative 1.73, approximately right there. At 3 pi on 4, so that's 3/4 of pi. And so in this case here, pi is divided up into 6 sections. So if you multiply 6 by 3 and divide by 4, then you'll get the decimal equivalent. And it's at negative 1 there, so it should be right there. And then at 5 pi on 6, it's at negative 0.58. At pi, we're at 0. At 7 pi on 6, we are at positive 0.58. At 5 pi on 4, we'll be at 1. At 4 pi on 3, which is 8 pi on 6s, we're at 1.73. And then at 3 pi on 2, once again, we are undefined, so we have another vertical asymptote there. At 5 pi on 3 or 10 pi on 6, we are at negative 1.73. At 7 pi on 4, we're at negative 1. 11 pi on 6, negative 0.58. And then at 2 pi, back to 0. Now, between those two asymptotes, and I'm going to draw this graph in black, this is one cycle of the graph. Between pi on 2 and 3 pi on 2, so I can put those values in there. This is at pi on 2, this is at 3 pi on 2. We have one cycle of the graph. The rest of these points are just continuation of this pattern. All right? So what happens is that now the period is only pi radians, because that is a distance between 1 pi on 2 and 3 pi on 2. If you subtract those, you'll get 2 pi on 2, which is pi. So that's one major difference between tangent and sine cos. The period is pi radians, or 180 degrees, if we're working in degrees. Also notice that there is no amplitude, because the amplitude is the distance from the middle to the maximum, or the middle to the minimum, and there are no max and mins. These graphs continue forever going upwards, getting closer and closer to the vertical asymptote here on the right, and go downwards forever on the left, getting closer and closer to the vertical asymptote. There is no amplitude. So the period is every pi radians. Every pi radians, there'll be one cycle of the graph. As well, every pi radians, there will be another asymptote. So our next asymptote will be at negative pi on 2, which is right there, and then negative 3 pi on 2, which would be right there. And the rest of the graphs can be drawn following this same pattern. We always put arrows on the end to show that that pattern continues. So there's the graph between negative 2 pi and positive 2 pi. So remember that for sine cos, the domain went from negative infinity to positive infinity. Not so here because we have those vertical asymptotes. When we state the domain here, it's going to be in terms of the restrictions that x cannot equal. Our domain will be x cannot equal, and we can start at any one of those vertical asymptotes that we want. Normally we start at the smallest positive, which would be pi on 2. That's where your first vertical asymptote is. So our domain is that x cannot equal pi on 2 plus every multiple of pi from there, because that's where all of the asymptotes are. Our domain here would be that x cannot equal pi on 2 plus n pi, where n is an element of integers. Whereas the range, this graph goes up and down forever. The range goes from negative infinity to positive infinity. But if you add pi onto pi on 2, you get to 3 pi on 2, right? So this statement gives us what x cannot equal instead of what x does equal, just because it's so much simpler to write the domain in that format. All right. You also may be asked to state the x-intercepts, and the first one is at 0, the next one is at pi, then 2 pi. As we go backwards, they'll be at negative pi and negative 2 pi. Our x-intercepts are at every multiple of pi. So we can say our x-intercepts are at n pi, where n is an element of integers. So those are the key characteristics for the graph of tangent. So in this case, we graphed it in terms of radians, but we can do the same thing in degrees. Remembering that our first asymptote was at pi on 2 radians, which is 90 degrees. And the next one was at 270 degrees. Remember, between those first two asymptotes is where we had one full cycle of the graph with an x-intercept at pi radians or 180 degrees. So there's the graph if we were doing this in terms of degrees instead of radians. So again, if we talk about the characteristics, there is no amplitude. Our period is 180 degrees. We would say that our domain now would be that x cannot equal 90 degrees plus 180 n degrees. That's where all the vertical asymptotes will occur. Our range still goes from negative infinity to positive infinity. And now we would say our x-intercepts are at every multiple of 90 degrees. Sorry, 180 degrees. 180 n degrees, where n is an element of integers. So we can do all the same transformations on the graph of tangent that we did on the graphs of sine and cos. You can vertically stretch these. It just means that the graph gets steeper faster, that's all. It's not going to change the amplitude because there is no amplitude. But you can still vertically stretch. They just get steeper faster. Or if the stretch factor is between 0 and 1, they would get steep not as fast. They can be reflected over the x-axis. They can be reflected over the y-axis. And they can be horizontally stretched. They can be shifted up, down, left, right. So in this first one, we want to sketch the graph of y equals tan 2x. But we will start with the base graph, which is the graph of y equals tan x. So let's start with that. We have our first asymptote at 90 degrees, our next one at 270. This is the graph of y equals tangent x. It has the first x-intercept at 0, then 180, then 360. So this is the graph of y equals tangent x. Has a period of 180 degrees. So now, for tan 2x, you've got a b value of positive 2. That's going to cause a horizontal stretch of 1/2. So everything will be half of what it was before. The period will be half of what it was before. The period will now be, instead of every 180 degrees, the period will now be half of that, every 90 degrees. Our first vertical asymptote will also be half of what it was before. So our first asymptote, which before was at 90 degrees, that'll be half as well. It'll be at 45 degrees. Okay, so let's draw our first asymptote. And let's use blue. It's at 45 degrees, right there. And because the period is now 90 degrees, the next asymptote will be 90 degrees from 45, which is 135 degrees, right there. The next one will be 90 degrees away from 135, which will be 225 degrees, right there. The next one will be 90 degrees from 225, which will be 315, right there. Remember before, the x-intercepts were starting at 0 and then every multiple of 180? Well, now they'll be 0 and every multiple of 90 degrees, half of 180. So we can make note of that as well. Before, the x-intercepts were at every 180 degrees. Well, now that's going to be cut in half as well, so now it'll be at every 90 degrees. So our first x-intercept will be, well, 0 will still be an x-intercept because half of that is still 0. But then every 90 degrees, which, are basically halfway in between the asymptotes. So this is what this graph will look like. Whoops. So there's the graph of y equals tan 2x. The domain will change. The domain for this will be x cannot equal, the first asymptote was at 45 degrees, and because the period is 90, now it's every multiple of 90 from 45 degrees. The range hasn't changed though, it still goes up and down forever. Okay? Then on the next page, sketch the graph of y equals tan of x minus 30 degrees plus 1 on the grid below. State the period, domain, range of the function. Well, this one has not been horizontally stretched. There is no b value. So the period will not change. Right? The period is still every 180 degrees. Once again, we can start with the original graph if we want, but it might make it a little bit convoluted. So maybe let's not graph the original graph, but we remember what it looked like. Remember that the original graph started at the point 0, 0. But this one has to go over 30 degrees to the right. And so we should write this down perhaps, that C equals 30 degrees. So therefore we have a phase shift of 30 degrees to the right. And we have a d value of plus 1. So there's a vertical displacement of 1 up. So the graph of tangent normally started at 0, 0, but now it's going to go 30 degrees to the right and 1 up. The first asymptote was normally at 90 degrees, but now it's going to be at 120 degrees. The period hasn't changed, so if you go 180 degrees from 120, that'll take us to 300. So normally the next x-intercept was at 180 degrees, but now it goes 30 degrees to the right and 1 unit up. So now it'll be at 210, 1. And then at 360, 30 degrees to the right and 1 unit up. And I have to guess where that one will be. This is what this graph will look like. And we we never really talked about it before, but what was happening at the x-intercepts on the previous one is that there was a point of inflection there. It's where the concavity of the graph changes. That's what that's called. So that's what that graph looks like. So in this case here, we're just asked to state the period, which we did, 180 degrees, but then also the domain and the range. So the domain of this would now be that x cannot equal 120 degrees plus 180n. Our first asymptote was at 120, but our period didn't change. And our range hasn't changed either. We're still going up and down forever from negative infinity to positive infinity. Okay? So there's assignment 5.3. Nope. I'm going to post the solutions on Google Classroom so you can check your answers. And at the bottom, it says on that first page to investigate what happens to the graph of y equals tan x as x approach 90 degrees. That's where that first vertical asymptote is. Then you're going to see why it approaches the asymptote like it does. Okay, so I will post the solutions to this to Google Classroom so you can check your answers. And then Monday we'll be having a quiz on chapter 5. Okay? Yeah, I think it's 2 pages back to back, right? Yeah.